Hello? Is that mic working? Perfect. Okay. So my name's Kieran. I'm from NCC Group. I'm going to talk about hardware basics, why and how to break hardware. So we're going to we've only got a small 25-minute slot, so we're going to cover why break hardware, specifically focus why software people should break hardware. So this talk is mostly focused towards people who've never really dealt with hardware at all. If you're a hardware person, probably you're not going to learn anything, but yeah, we'll see. So we're going to cover tools, specifically things in your hands versus tools that we software people normally think of. We're going to specifically cover how to get a serial connection on some sort of like IoT device or similar. The intention here is that if you leave this room, you should be able to take a device, break it out of the case, and find and connect to a serial connection. And if you can take that away from here, you're good to go. One of the biggest problems with hardware is that a lot of the stuff that's researched, or that the bigger boys have done, getting to that level is virtually impossible. And it's hard to find baby steps in hardware. There's tons of guides for how to learn to do web apps and stuff. With hardware, you tend to have electrical engineering, like learning about resistors and logic gates, which is kind of super basic, and then there's jumping straight into way advanced topics that it's hard to find a middle ground. So you can leave here and you can do a serial connection, great. We're going to briefly cover firmware, jtagging, and side channel stuff. We don't have time to do proper dives on this stuff. We've only got a small slot, so we're just going to kind of give these other topics a bit of a tickle. Hopefully you guys will be so excited about it that you'll go away and do a bit more learning on those things. So my background is Abertay grad, 5 years-ish pen testing, just over 5 years. Mostly a web app inf tester guy. The point of this slide is to point out that I'm not hardware. Like I came from a normal pen testing background, and I still suck at hardware, but I'm getting better at it. So in the wise words of Jake the dog, sucking at something is the first step towards being kind of good at something. I'm CTL. If you're not from the UK, that won't mean much to you, but that's fine. So why break hardware? Specifically, why should non-hardware people learn about breaking hardware? IoT is everywhere. Devices are coming thick and fast, and we know that they're not very good. Like the APIs generally are not locked down very well, and there's all sorts of bugs to be found. It's not just the software side that's going wrong. A lot of these vendors, they're new to this stuff and they're making basic mistakes. A lot of vendors who know about hardware are not making mistakes anymore, but now we have all these new devices coming on the market. There's all sorts of problems. So the target-rich environment. The main point for having non-hardware people learn about hardware is the fact that you can effectively turn what is a black box assessment into a white box, by which if you have a root shell, you can pull down binaries and you can get like a web app or something. You can pull it straight down and analyze it offline versus trying to bash your head against whatever the target is. And a lot of the heavy lifting has been done by hardware people who, as soon as they get a root shell, they're done. Like that's the hardware things, get a root shell, hey, I'm finished. Whereas for software people, once they have a root shell, they have access to the device. And lots of people are scared of it, which means that there are fewer people doing it. So that sounds great, but hardware is expensive. It's kind of a myth. Getting into hardware is not expensive. You only really need a multimeter, a USB TTL, a USB serial converter, one of these guys. You can pick these up on eBay for like $5. A soldering iron and some wires, some jumper cables. A breadboard would be handy, but you can get cracking for $20 to $50. $20 to $50 is not going to buy you good equipment. Let's make that clear. But if you're just starting out, that's fine. You don't need good equipment yet. There are all these really cool, shiny tools that everyone wants to talk about. And these are cool, shiny tools, but you don't need to dive in and buy these stuff straight away. Unless you have a use for them, there's no real reason to just dive and buy these straight away. The one sort of exception is logic analyzer here. There are, to buy a logic analyzer, you're looking at maybe $100 plus from a proper vendor. Hypothetically, it may or may not be possible to download the software for the logic analyzers from a reputable vendor and then buy a Chinese knockoff, which would put the logic analyzer back in this slide, but I can't confirm or deny whether that would be feasible or whether that would work. FPGA is a really cool tool. It allows you to effectively build your own tools, field programmable gate array. We're going to talk about that very briefly later on. So, serial connections, let's dive straight in. So, serial connections are on all sorts of things, they're everywhere. They're used by embedded developers to debug their boards when they're being made, and so we can do exactly the same thing. Can provide you access to a bootloader, and it allows you to view the boot process as it happens, which can then give you some clues later on, which hopefully at the end of it will give you an interactive shell. So we're going to specifically talk about the UART. Universal Asynchronous Receiver Transmitter. Universal is obvious, it works on all sorts of chips. Asynchronous just means there's no external clock. If you don't know what that means, it doesn't really matter. Receiver transmitter means that there's two-way communication, so that there's an individual transmit pin and an individual receive pin. And essentially, it allows the chip receiving all of its information in parallel, and it just allows you to access that across one wire. And effectively just allows us to talk to the device. So, to find a UART, the first stop is just going to be crack open the case, which caused us problems about half an hour ago when I got the lid stuck on here. And you're just going to look at the thing. You're going to be looking for probably 4 pins in a line. There's no guarantees. Manufacturers do weird stuff. Sometimes the UART isn't nicely laid out for you. But yeah, hopefully you're going to have 4 pins in a line. So this is a device that's just like a travel router that I had lying around that was going to be like a poor man's Wi-Fi pineapple, and it ended up just not becoming anything. So it was lying around. So on here you're going to look at this. This is this. So I got a bit lucky here. This was like my first try at pulling stuff apart, and there's a UART port right there, or what looks like a UART port right there. You have 4 nice pins laid out, and yeah, so that's a pretty good indication. That's probably the kind of thing we're looking for. So from here, we're going to work on the assumption that that is exactly what we're looking for. But we need to work out which of these 4 pins is what. So you can do this, again, like I said, the point of this talk is that you can do a lot of this stuff on a budget. So the proper way of working out these pins is with a logic analyzer. But if you don't have one, there's a kind of ghetto way of doing it with a multimeter. So you stick your multimeter to continuity mode, or into its continuity setting, and then effectively all it does is when the circuit is complete, you get a beep. So you're going to take one probe and pop it on a ground somewhere, like a shield on this device, and then you're going to point the other probe and poke it in the holes, and when you get a beep, that's the ground. A quick kind of guide is see the 3rd pin. So P1 is labeled. So P1 at the top, and the 3rd pin has kind of a cross on it. On the slide, it's really easy to see. In real life, it's much harder. If you can see that on a pin, that's going to be your ground. But check anyway. So once you've got your ground, you're going to plug the device in, turn it on, and then you're going to, using your multimeter on the voltage setting, you're going to stick one probe in the ground, either the one you just found or the shield, doesn't really matter, and you're going to prod the others. Whichever one is running at the voltage of the device is the one you want. So probably 3.3, but it doesn't necessarily have to be. So the transmit pin is transmitting data. So any digital signal is going to be a nice square signal, right, where the transmit pin is turning off and on. It's going from 1 to 0, which means it's going from 3.3 down to 0 and 3.3 to 0, which on your multimeter is going to give you an average voltage of something like 1.0 and 2.5 volts, depending on how much data is coming out of the thing. RX is sometimes slightly harder to work out because vendors do slightly weird things. So on this particular device, when TX goes low, so when on the trailing edge of the signal, RX goes high, very, very briefly, which I think is a grounding issue. But I went and bought another one of these because I thought, oh, maybe it's my device, and they both do it. So maybe it's a grounding issue with the device. I don't know. If you've got logic analyzer, it's going to make it super easy. Again, your RX isn't necessarily going to be easy to work out, but the TX is going to have a nice square signal depending on how much data is coming out at the time. You can also just look at the data sheet of the chip and follow the lines for which pin is which. If these handy tip here, I've actually had another handy tip from this fine gentleman with the blue t-shirt. Sometimes these pins are full of solder when you get the board. Don't try and desolder them. Either drill them out or melt the solder and use a desolder vacuum pump thing to pull the solder out, because if you try and melt all the solder, you're just going to melt your board and have a bad time. Okay, so connected to the UART. So I have a quick video. Not this one. Okay. Oh, no, now I can't see it. Where the hell's the mouse? Okay, that's fine. So we're just going to use a screen command, tell it which device we're pointing at. That is this USB serial converter. And you're going to have your TX pin on here wired to the RX pin on the device and vice versa. And we're going to set the baud rate, which kind of flashed away pretty quick there. But so the baud rate is just the frequency, the speed at which you're going to speak to the device. There are a few different baud rates. That's probably the most common. There are tools out there that will, like baud finders, where it'll try and brute force. If you get the wrong baud rate, you'll just get garbled output. Nothing bad is going to happen. So see here where it says at the bottom, auto booting in 1 second. That's relevant later. We'll come back to that. So all this kind of garbage comes spitting out. Like I said, sometimes you get clues here about another way to, if this isn't easy for you, if you don't get dropped into a shell, sometimes looking through the output here can give you some clues of how you might be able to break the thing. So if you're lucky, you'll get dropped straight into a root shell. In this instance, that isn't the case. You get a login prompt. I started writing a serial brute forcer for this, and then I found that the creds are online. And a lot of vendors use the same creds across everything. So once you've got a vendor's creds, often they'll be used across all their devices. So from here, you can kind of check what you've got a stripped down shell here. It's not like a full Linux distro, but we have access to TFTP in a second. And so you've got a method to pull files off and do whatever else you want to do. So there's TFTP at the bottom. So yeah, that's great. We win. Okay. The slides are here, by the way, just so that this still makes sense without the videos. So yeah, if you're lucky, you'll get a root shell. Maybe not. So that's great. We've got a shell. You can hopefully go do this and be really inspired to do all these other things. So firmware. To get our hands on firmware, we've got a few different options. U-boot is one potential way of getting access. That part where it was saying auto booting in 1 second, a lot of the time it's possible from there to boot into a U-boot console. There was a U-boot talk like just before here. They probably discussed this way better than I do. So if you hit the escape key, you potentially get dropped into U-boot or some other command. So for this particular device, you have to type TPL because it's a TP-Link device. I think they had like a glitching technique to skip that, unless yeah. Another way to grab firmware is via JTAG. So again, it's another hardware debug point that's potentially accessible. Provides access to the firmware, but it does all sorts of other cool things, which is why it's on device. So for example, it's possible to do like a border scan to make sure each of the pins are soldered correctly. You can also physically remove the fast chip. So this is kind of in order of difficulty here. And there's also a few other like crazy ways of doing this, but again, baby steps. And then once you've got the firmware, you can reverse engineer it. That's like way outside the scope of this talk. So again, finding the thing, back to looking on the board again. You're probably looking for a 2x5 or 2x10 pin array. Manufacturers do weird stuff here. And sometimes you don't actually have access to the pins at all. They're not in a nice array here. So the perfect example, I said manufacturers do weird stuff. You're probably looking for X and Y. This isn't a 2x5 or a 2x10. It's 2x6. But anyway, the pins you're looking for are TDI, TDO, TCK, and TMS. There is no handy-dandy way of working these out with a multimeter or anything. So you're going to be looking probably for like a JTagulator is going to be your best bet to determine which one is which. However, you can read the data sheet and work out, and on the data sheet it will tell you which pin is which, and then you can just hopefully just trace the lines back and work out where they go. Even if you don't have a handy pin out here, often you may have seen PCBs with wires soldered seemingly randomly to the board. If you can just follow the trace from the pin to where it goes on the board, then you can just solder straight onto the trace using some super fine wire like speaker wire or something is the best thing. So that's JTAG and firmware. Like I said, we don't have time to do it properly, but there we are. So side channel is all about thinking outside the box with my handy visual demonstration where you have to join up all the dots using only 4 lines, and the only way to do it is to go outside the box. So split mostly into 2 categories. You can split these lots of different ways. The way I prefer to split is passive and active. So passive, you're measuring something. Probably even with passive stuff, you're going to have to physically interact with the board. You're going to have to make changes to the board. But you're not changing anything on the chip as it's happening. You're just measuring certain things. And then you've got active side channel attacks where you're physically making changes to the chip as it's running. So maybe you can, like, again, a lot of this stuff are really high-level stuff that are like crazy, legit crypto analysis stuff. But the point here is that they don't have to be. A lot of these stuff aren't necessarily out of the reach of people just starting to learn about this stuff. So, timing attacks. You're going to analyze the time taken to complete a task. Like I said, this is used for like genuine crypto attacks, but it can also be used against like a bad password or PIN implementation. You're going to measure the time delay between the password you give it and the response saying, no, you got the wrong password or the wrong PIN or whatever. So I actually half considered bringing a safe to demonstrate this, but it wasn't logistically feasible. So it's basically just a fancy brute force attack. So here we have a giant diagram where you can imagine this is some sort of string compare function on a pin code where it checks each character in turn. So if you get the first character wrong, you get thrown out straight away. If you get the first 3 right and you get to the 4th character, you've gone through more code. So there's more time, there's more code to go through, which takes longer. And so if you can measure that accurately enough using something like an FPGA, potentially you can infer data back. So in this example, the pin on the target is, let's say, 1, 2, 3, 4. So you send 0, 0, 0, 0, and you get a response back in 50 nanoseconds. That doesn't tell you anything. You've got only 1 data point. So then we try 1, 1, 1, 1, and then we get a reply back in 70, which means we've got something right. We don't know whether we've got 1 or 4 right at this point. So we'll try 1, 0, 0, 0, and we get a response back in the same time, which tells us, OK, we've only got 1 right because it matches. And then we try 1, 2, 0, 0, pardon me, and again, at this point, we still don't really know whether we've got 2, 3, or 4 right. Well, we've got 4 right because we've got it incorrect. But we can infer that probably we've only got the first 2 because the time delay is very similar. Your time delays probably aren't going to line up that neatly in real life, but it's just a kind of a quick example. So glitching or fault injection, same thing, depending on who you speak to, who you learned it from. We're going to tamper with the chip, potentially force skipped instructions. This technique can also be used to like zero out registers and things like that with like very precise EM. That's like high-end stuff. But you can kind of make this work on a budget. So this example is going to work with the FPGA that I have here, which is like 25, maybe $30 or something, using the open source Ice Storm toolchain. So manufacturers will go out of their way to try and stop accidental glitching. With voltage glitching, you're probably going to have to make modifications to the board, or potentially just lift the pin and access it directly, because manufacturers know that messing with voltage is going to mess with their chip. So they'll try and stop natural EM or whatever else that could cause problems. So you're going to have to undo a lot of that work to make this work in real life. And yeah, this is probably going to require a lot of trial and error. So this is a very quick POC that a friend of mine named Mr. Dean Jerkovich helped me put together. So on the right is just an Arduino. So there's an Arduino chip with the Atmega chip off the board, and then the Arduino, and then you just run jumper cables from the chip to the board. So this is still connected, but you then have access to interact with the power line or the ground line or whatever. So on the left is just a quick sketch that's doing some basic maths, because at this point we didn't really know how the glitching was going to work. And then it just outputs the serial on the right there. So that just kind of carries on for a little while. Where's my mouse? And then we're going to upload quickly. The FPGA at this point is driving another transistor on a separate board. I'll show you the Verilog in a second. But so when you run the glitch binary, it uploads that code to the FPGA. And so what that will do is periodically cut the power to the ground line which we've intercepted, which will then effectively turn so that's the Verilog, which will turn the power off to the chip very quickly, but not quick enough that the power dies. So it doesn't die, it just messes up what it's doing at that point. So very briefly, so this is Verilog, which is it's not a coding language, it's more of a hardware description language. So essentially all it's doing is creating a counter and then cutting the power for the glitch duration, which is defined as 75. So it's just 75 cycles of the counter. So nothing actually happens here for quite a while. This method is obviously a pretty rubbish way of doing things because you have no control over when your glitch is going to happen. If you have some sort of trigger mechanism, which is what the chip whisperer is like perfect for, to be honest, but again, chip whisperer is an expensive device. This proves that you can make glitching work on a budget. So at the bottom, it's just kind of gradually updating. Where the hell is my mouse? Here it is. If we fast forward a bit, this is going to be such an anticlimax. Ready? Here it comes. So this is why I didn't want to do a live demo, because this is completely, more often than not, this will just brick the device and it will just stop transmitting at all. It definitely does it. There we go. So here it's messed with the counter and then it carries on, which is exactly the kind of thing we want. We don't want to kill the device. We just want to make it do something. And in this instance, we have virtually no control over what it actually does, which is unfortunate. But it's a basic example that proves glitching can work on cheap devices on a budget. Okay. So on that instance, we're going to assume that the previous example with the timing, that's pretty easy to defeat that. You just add in, instead of checking individual string, each character individually, you check the entire string together, or you hash it, or you do something like that. In that instance, something like glitching would be perfect, because potentially we can skip that check and jump straight to do the thing. If we can skip that instruction and time it correctly, then we can jump in and away we go. So, to summarize, getting started is relatively easy. It's not as complicated as you think. There are baby steps that you can do to kind of jump in. There's a whole bunch of resources out there to help, but they are harder to find than for, say, like web app testing or whatever. OpenWRT are a bunch of folks who are like hell-bent on getting open source firmware on every single thing in the whole wide world. And exploiteers are a bunch of guys who've done some crazy DEF CON talks, but a lot of their guides on the wiki are quite easy to follow. And it's fun, and there's bugs. So yeah, oh man. There we go, that's me. That's me, that's my email, that's my Twitter that I don't really use, but feel free to tweet me. And yeah, that's us. Thanks a lot.